In this lesson, we'll review the action of the parallel RC circuit and discuss all of the factors that influence the circuit's operation. Now, perhaps it's difficult for you to realize the importance of RC circuits, but you can believe me, they become more important as you progress through the course. Later, you'll see RC circuits used to control frequency and phase relation and timing circuits. So let's examine the parallel RC circuit. Now, as you know, the resistor never introduces a phase shift in any circuit, while the capacitor causes a phase difference between current and voltage in any kind of circuit connection. Now, this phase difference may be shown with vectors. In parallel as in series, the voltage is the reference vector. Remember, the voltage across a parallel branch is the same. Thus, EA becomes the reference vector. The branch currents will show the phase differences. Now, since we're concerned with parallel RC circuits in this lesson, let's examine a circuit with given component values. We'll calculate the branch currents and plot this information vectorially on our graph. Now, the current through each branch can be easily determined by simply applying Ohm's law. For example, IR may be found by dividing the resistance into the voltage, or 120 volts over 4 k ohms gives us a total current through the resistive leg of the circuit of 30 milliamps. Thus, the vector for IR will show the value of 30 milliamps on our graph, and also the 30 milliamps of resistive current must be shown in phase with EA, since the resistor does not introduce a phase shift. Now, the capacitive current, or IC, may be found in exactly the same way, simply applying Ohm's law. In this case, IC is equal to the voltage over the capacitive reactance. 120 volts over 3 k ohms equals 40 milliamps. And the vector for IC, or our capacitive current, will show 40 milliamps 90 degrees ahead of EA, because the capacitor introduces a phase shift. Now we can draw our parallelogram and find the approximate total current by simply measuring the length of the resultant vector. In this case, if we measured the resultant vector, it would be 50 milliamps, or IT is 50 mils. Now, the reason these two currents cannot be added together is because they don't occur at the same time. We know that IC and IR are 90 degrees apart. And if we plot the waveforms of these two currents, we will see that the sum, or the resultant current, will be greater than either of them, but less than the arithmetical sum. For example, at 0 degrees, IC is 0 and IR is 30 milliamps. So the current in the circuit would be 30 milliamps. 45 degrees, IR is now about 25 milliamps and IC about 25 milliamps. Thus, the resultant, or the total current, would be 50 milliamps. And at 90 degrees, we see that IR is 0, IC is 40 milliamps, so that would be the value of the resultant current, and so on throughout the rest of the cycle. And we find that the total current is greater than either of the branch currents and less than the arithmetical sum, and also the phase difference is something less than 90 degrees. Now, the approximate phase angle may be found by simply measuring angle theta, which is the angle between the total current and the reference, or EA. And we can measure the angle simply by applying a protractor to the schematic, or the vector drawing, and we see that the approximate angle is 53 degrees. However, we know that the exact angle is 53.1 degrees. And you can see that the graphical solution for these values is approximate at best and would be difficult to handle in a more complex circuit. Now, impedance vectors are not used in this parallel circuit because a series equivalent would first have to be developed, and for our purposes, it's much simpler just to apply Ohm's law. And when we apply Ohm's law, we see that ZT is equal to EA over IT, or 120 volts over 50 milliamps, and the total impedance in the circuit is equal to 2.4 k ohms. And as in all parallel circuits, the total impedance is less than the smallest impedance in the circuit. Now, thus far we have seen that the graphical solution of the problem is not very accurate and would become difficult to handle in a more complex circuit. The next portion of this lesson will point out a much more accurate and easier way to calculate the unknown factors in our circuit. First of all, we'll find the current in each branch as we did before, and we'll draw the vectors that represent these currents, show their values and their phase relationships. But before we go on to solve this problem, let's first relate the vector representation to the familiar right triangle. And we can see that IR is the same as the adjacent side of this triangle. IR compares to the adjacent side. IC compares to the opposite side. And IT would equal the hypotenuse of the triangle. Now, since the vectors of the circuit currents, I should say, are so closely related to the sides of the triangle, the same geometric theorems can be applied. Thus, side C, the hypotenuse, is equal to the square root of side A squared plus B squared. Therefore, IT, or the total current, is equal to the square root of IR squared plus IC squared. Now, of course, this method is much more accurate than measuring the vector on the graph. And we can also see that the size of angle theta is determined by the size of the sides of our triangle, or by the amount of IC and IR. Now, the relationship of the sides of the angles have been calculated for almost every angle and put together in a table called trigonometric functions. Now, the table of trig functions that are true for triangles are also true for our vector diagram and are a great help in solving even the most complex circuits. Now, these relationships are called the sine, cosine, and tangent, and they may be used to determine the angles of the triangle or the phase angle of our currents. Let's see how these relationships are derived. The sine of angle theta is found by dividing the opposite by the hypotenuse, or IC over IT. The cosine of angle theta equals the adjacent side over the hypotenuse, or IR over IT. And the tangent is equal to the opposite over the adjacent, or IC divided by IR. Now, in each case, when the division is accomplished, the sine, the cosine, or tangent will equal a whole number or a decimal fraction that may be used to locate the phase angle in the trig tables. In other words, when we solve for the sine, cosine, or tangent, we're finding the ratio of one side to the other, or one current to the other, which of course determines the angle theta. And if we take this number to the trig tables, the angle may be found. For example, if we wish to use the cosine to find angle theta in this circuit, the formula cosine equals the adjacent over the hypotenuse, or IR over IT, which would be 30 milliamps over 50 milliamps, and the cosine of angle theta would equal 0.6. Now, the only way that the cosine 0.6 will give us angle theta is in the trig tables. And we know the approximate phase angle is 53 degrees. So we'll go to the trig tables and find the cosine nearest 0.6, which is 0.6004, and we see that the angle is 53.1 degrees. The procedure is very simple and very accurate. But now that we have the phase angle, what are we going to do with it? Why all this concern over phase difference between current and voltage? Well, it's very difficult to show you the specific reason that phase shifting networks are important, but you can count on finding this principle used in many types of circuits. For example, a network similar to this one is used to start a split phase motor, and in some cases will determine the efficiency at which the motor operates. And the phase angle also gives us an indication of the power factor. Power factor, you recall, is the ratio of energy actually dissipated to the total power supplied to the circuit. In other words, the power factor simply indicates what percentage of the power supplied to the circuit is dissipated as heat. Now, this point may be understood by looking at our circuit in operation. When the first alternation occurs, current flows through the resistor and heat is generated, or we dissipate power. Current also flows to the capacitor, but the energy is stored in the capacitor and not dissipated. On the next alternation, current flows through the resistor in the opposite direction, and power again is dissipated. But the capacitor simply returns the energy stored, and again no power is dissipated in the capacitive branch. Therefore, only the resistor dissipates power, but both components draw current. Now, from our previous calculations, we have found that IR is equal to 30 milliamps. Thus, if we apply the power formula, P is equal to I times E, we find the power dissipated in the circuit is 3.6 watts. Now, this is true power, the power actually dissipated by the resistor. However, if we apply the power formula to the entire circuit, we find that since we must use total current, or 50 milliamps, and EA, of course, is 120 volts, then the circuit apparently uses 6 volt amperes. And you recall that apparent power is measured in volt amperes rather than watts, because all of this power is not dissipated as heat. Now, the ratio of true power to apparent power is the power factor. And stated mathematically, power factor equals true power over apparent power, or 3.6 over 6 equals 0.6. The power factor for our circuit is 0.6. Also, since the currents in the circuit tell us the amount of power in each branch, we can use the power factor, the ratio of these currents to determine the power factor. IR over IT, 30 over 50 equals 0.6. The power factor again is 0.6. Also notice that the cosine of angle theta equals IR over IT, or the cosine of theta equals the power factor. And now we can see how the phase angle will influence the power factor, or influence the efficiency of our circuit. For example, if the circuit were purely resistive, the power factor would equal 1, because IR would equal IT, the true power would equal the apparent power. But if a reactive current were introduced, or if the reactive current were increased, then total current would increase, angle theta would increase, and the power factor would decrease. Of course, apparent power would increase also, causing the power factor to decrease. In other words, as the reactive current increases, we demand more current than we're actually dissipating in the form of heat. And this is one of the reasons that the power companies watch the power factor very closely. It's possible to imagine the apparent power far above what we're actually dissipating as heat. Let's review the facts we've discussed within the last few minutes. First, we saw that EA, or the voltage applied, was used as the reference vector. And the phase difference in this circuit was shown by the branch currents, IR and IC. And the branch current values were determined by applying Ohm's law. The approximate total current could be discovered by measuring the resultant vector on the graph, or, more accurately, by using Pythagorean's theorem. Total impedance in the circuit was found by using Ohm's law also. And the phase angle can be determined, once again, by simply measuring the graph, or, more exactly, by calculating the sine or cosine of angle theta, or the tangent, and using the trig tables. The phase angle is important to us because it gives us an indication of the power factor, which we define as the ratio of true power to apparent power. Now, the facts we've discussed concerning this circuit will become more important to you as you gain additional knowledge of their application, so know them well.